Hi, Hola, Bonjour, Salaam. Welcome to Blueprint Bazaar. Today we are diving into a comprehensive industrial simulation challenge using Simio software, specifically focusing on the optimization of a mobile entity system. When we look at modern manufacturing, the efficiency of how parts move through a facility is often dictated by the logic of our transport systems, and in this case, we are examining a classic palletized loop. The process begins with the arrival of individual pieces, where the timing is not fixed, but rather follows a uniform distribution between 0.75 and 1.25 minutes. This stochastic arrival rate ensures that our model accounts for the natural fluctuations found on a real shop floor, where one arrival corresponds to a single piece. Once these pieces arrive, they must be secured onto pallets through a process called mettre en palette. According to our parameters, the time required to set or detach parts from a pallet is uniformly distributed between 10 and 20 seconds. This means every time a part enters or leaves a pallet, there is a small but significant delay that can lead to bottlenecks if the flow of empty pallets is not managed correctly. The core of the value-added work happens at the traitor or treatment station. Here, the operative time required to treat a single piece follows an exponential distribution with an average of 0.9 minutes. It is important to note for our fellow engineers that if we are processing multiple pieces on a single pallet, the total time for that pallet follows an Erlang distribution based on the number of pieces n and the parameter mu. After the treatment is completed and the pieces are detached to become a produit fini or finished product, the empty pallet doesn't just disappear. It must make the retour de la palette, or the return trip, to the beginning of the line to pick up new arrivals. This return journey is also stochastic and follows a triangular distribution with parameters of 5, 15, and 25 minutes. This wide range in return times introduces a layer of complexity because it means that even if we have many pallets, they might all be stuck in the return phase at once, leaving the loading station empty and causing a backup of parts at the arrival point. Our mission today is to act as system optimizers for Blueprint Bazaar by answering two pivotal questions. First, we must determine the exact number of pallets that should be in circulation as a fixed number. Second, we need to decide on the physical capacity of those pallets, choosing between 2, 4, or 6 pieces per pallet. These decisions cannot be made in a vacuum. They must satisfy two very strict performance criteria provided in our practice problem. The first constraint is throughput. The system must be capable of producing exactly 55 finished products per hour. The second constraint is the lead time, or the average time a part spends in the system, which must be kept to a maximum of 1 hour. This creates a fascinating trade-off for us to explore in Simio. If we increase the number of pallets, we might increase our throughput, but we risk cluttering the system and increasing the time a part spends waiting in queues. As we build this out in the Simio environment, we are looking at a mobile entity system where the parts are the entities and the pallets are the transporters. We will be using the Experimenter tool in Simio to run multiple scenarios and find the optimal configuration. We'll set up a table to test different combinations of pallet counts and capacities to find that sweet spot where we hit our target of 55 units per hour without exceeding the 60-minute time-in-system limit. This type of analysis is exactly what makes discrete event simulation so powerful for smart manufacturing. It allows us to fail fast and iterate in a digital environment before ever spending a dime on physical hardware. We have to be mindful of the stochastic nature of the return times and the processing times, as a single lucky run isn't enough to prove the system works. We need to look at the average results over many replications to ensure our solution is robust. To build this in the Simio environment, our first step is to define our mobile entities. We add two model entities to the workspace and name them pallets and parts, respectively. To bring these into the system, we add two sources, one dedicated to pallets and the other to parts. We then lay out the functional blocks of our production line by adding a combiner to represent the palletizing station, a server for the treatment process, a separator for detaching the parts, and finally, a sink to collect the finished products. Part arrivals at their source are defined by a uniform distribution between 0.75 and 1.25 minutes. This setup ensures that our model accounts for the natural fluctuations found on a real shop floor, where one arrival corresponds to a single piece. With our objects in place, we must establish the logical flow of the system using connectors and paths. We start by drawing a connector from the pallet source to the parent input node of the combiner. Simultaneously, we draw a connector from the part source to the member input node of the combiner. The time required to set parts onto a pallet is uniformly distributed between 10 and 20 seconds. This setup ensures that the pallets act as the carrying vessel for our incoming parts. Once the palletizing is complete, we use a connector to link the output of the combiner node to the input of the server node, where the operative treatment occurs. The operative time for a single piece follows an exponential distribution with an average of 0.9 minutes. Following the treatment, another connector is placed from the server output to the input of the separator node, where the parts will be removed from their carrier. The detaching process also follows a uniform distribution between 10 and 20 seconds. The final stage of our routing involves managing the output and the recycling of our mobile entities. We draw a connector from the separator's member output node directly to the sink input node, representing the completion of our finished products. However, because our pallets are a fixed resource in a loop, we cannot let them disappear into the sink. To handle this, we link the separator's parent output node back to the combiner's parent input node using a time path. This allows us to model the return of the pallets, which follows a triangular distribution of 5, 15, and 25 minutes. Our mission today is to act as system optimizers by answering two pivotal questions. First, we must determine the exact number of pallets that should be in circulation as a fixed number. Second, we need to decide on the physical capacity of those pallets, choosing between 2, 4, or 6 pieces per pallet. These decisions must satisfy two very strict performance criteria. The system must produce 55 finished products per hour, and the average time a part spends in the system must be kept to a maximum of 1 hour. This creates a fascinating trade-off. If we increase the number of pallets, we might increase throughput, but we risk increasing the time a part spends waiting in queues. By the end of this simulation, we will have a clear, data-driven recommendation on how to configure this production loop for maximum efficiency based on the provided mathematical distributions. We will look at how the Erlang distribution applies to the total treatment time. As pallets carry multiple items, ensuring we accurately predict if our pallet capacity choices will meet the production requirement. It is vital to ensure that the palletizing and detaching times are accounted for in the total 1-hour maximum lead time. Once we have these figures, we can confidently finalize our design for the mobile entity system. To finalize our model setup in Simio, we move into the Definitions tab to create the logical parameters that will drive our optimization experiments. First, we head to the Properties section and select Standard Property from the drop-down menu to create two expression properties. We will name these num pallets and pallet capacity. By defining these as properties rather than fixed numbers, we allow the Simio Experimenter to automatically swap values during our trial runs to find the best configuration. Next, we need a way to track our production in real time, so we go to the States pane and create a new integer state variable named part count. This state variable will act as our digital counter, incrementing every time a part reaches the sink, allowing us to verify if we are hitting our target of 55 finished products per hour. Once these are defined, we go back to the facility view to apply them to our objects. We select the pallet source and set the entities per arrival or initial number in system to reference our num pallets property. Then, we click on the combiner and set its batch quantity to reference the pallet capacity property. This ensures that the pallet will only move to the treatment server once it has collected the exact number of parts we are currently testing, whether that is 2, 4, or 6. With these properties and states integrated into our model, we have successfully created a dynamic simulation environment. This structure allows us to mathematically account for the Erlang distribution during treatment, as the server will now process a batch of parts based on our capacity property, while keeping the total time in the system under the 1-hour limit. We are now ready to run the experiments and find the most efficient setup for the system. Once our dynamic properties and state variables are fully integrated, we transition to the Experiments tab to evaluate the system's performance. In this environment, we define our primary responses, which act as our key performance indicators to ensure we meet the design criteria. We create a response for throughput to track the number of finished products per hour, another for the number in system to monitor congestion, and a crucial response for time in system to verify that the average time a part spends in the loop does not exceed the 1-hour maximum. Each response is mapped to its corresponding model expression, such as the part count state we created, or the built-in Simio tallies for entity lead times. With our responses defined, we set up several scenarios to test the interaction between our num pallets and pallet capacity properties. We can create 2 to 4 distinct scenarios, varying the pallet capacity between 2, 4, and 6, while adjusting the fixed number of pallets in circulation. This allows us to observe how the stochastic elements, like the triangular distribution of the pallet return or the Erlang distribution of the treatment station, impact our targets under different loading conditions. For instance, a scenario with 6 capacity pallets might increase throughput, but could potentially push the time in system past the 60-minute limit due to the time spent waiting for a full batch. After configuring these scenarios, we run the experiment across multiple replications to account for the randomness in our uniform and exponential distributions. Simio will process these iterations and provide us with a statistical summary of the results. By comparing the output data, we can identify which scenario successfully achieves a throughput of 55 products per hour while maintaining a lead time of less than 1 hour. This data-driven approach allows us to finalize the system design with confidence, ensuring the mobile entity system is fully optimized before implementation. Once we have run our experiment, we move to the results table to identify the optimal configuration for our system. We locate our specific scenarios and carefully note down the data produced for our primary responses. In the Simio interface, pay close attention to any red highlighting in the results. These red cases serve as immediate visual indicators that a specific constraint has been violated, meaning the configuration is not a valid solution for our problem. For example, if a scenario yields a throughput of only 53 products per hour, it fails to meet our strict requirement of 55 finished products per hour. Similarly, if the results show that the average time a part spends in the system is 2 hours, this is a major failure because our limit is a maximum of 1 hour. Such a result would be considered wrong or undesired because it exceeds the lead time threshold by double the allowed amount. We must sift through the data to find a scenario where the throughput is at least 55 units and the time in system stays safely under 60 minutes. This often involves a delicate balance between the number of pallets in circulation and their individual capacity. Once we find a line in our experiment results that satisfies both conditions without any red warnings, we have successfully optimized our mobile entity system. In the world of simulation, Simio stands out because it blends object-oriented modeling with a process-driven approach, allowing us to build digital twins that are both flexible and highly detailed. Unlike older software that relies purely on coding, Simio uses intelligent objects that have their own built-in logic and behavior. When we talk about extra knowledge for your projects, it is essential to understand the difference between properties and states, which we used in our last setup. Properties, like the ones we set for pallet capacity, are input values that stay constant during a simulation run, whereas states, like our part counter, are dynamic variables that change as the model executes. Another powerful aspect of Simio is its ability to handle stochastic variables, which is just a fancy way of saying randomness based on probability. In our pallet problem, we utilized various distributions like the uniform, exponential, and triangular distributions to reflect real-world uncertainty. If we assumed every part arrived exactly at 1 minute, we would miss the potential bottlenecks that occur when 3 parts arrive nearly at once. By using the Simio Experimenter to run hundreds of replications, we aren't just getting one answer. We are getting a statistical confidence interval that tells us how often our system will hit that 55-unit target in the face of random variability. Moving beyond the basic distributions, it is essential to understand how Simio handles the logic of entity movement through the connectors and paths we have established. In our model, the parts, entities, follow a uniform arrival distribution, but their progression is dictated by the availability of pallets at the combiner. By utilizing the specific logic where the pallet source links to the parent node and the part source links to the member node, we create a dependent relationship that mirrors a real-world assembly line. The time path we used for the pallet return is particularly important because its triangular distribution, stretching from 5 to 25 minutes, introduces the most significant stochastic delay in our system. If the pallets don't return fast enough, the part source will experience a backup, even if the treatment server is sitting idle. To truly optimize this, we rely on the mathematical relationship between our entities and the server. As the problem notes, while individual treatment follows an exponential distribution, the total time a full pallet spends at the server follows an Erlang distribution. This is where our pallet capacity property becomes a game changer. If we choose a capacity of 6, the server stays busy longer, but the parts at the front of the batch wait significantly longer to be processed, potentially pushing our time in system past the 1-hour limit. By monitoring the part count state variable, we can see exactly how these batching decisions ripple through the system's performance, allowing us to find the configuration that hits that 55 unit per hour sweet spot. The final step in our analysis is the careful review of our experiment results to ensure we haven't violated any constraints. When we look at our scenarios, we aren't just looking for high numbers, we are looking for valid numbers. Any scenario highlighted in red in Simio indicates a failure to meet our targets, such as a throughput of only 53 or a time in system exceeding 60 minutes. Once we find that perfect configuration where all our responses, throughput, number in system, and time in system, stay within the green, we have successfully optimized our mobile entity system. This rigorous testing process ensures that our design is not just a theoretical model, but a robust solution ready for a real smart manufacturing environment. That wraps up our deep dive into the optimization of mobile entity systems in Simio. By mastering these distributions and property-based experiments, you can tackle even the most complex industrial bottlenecks. We hope this breakdown helps you streamline your own simulation projects. This is Blueprint Bazaar. Thanks for watching and keep building. Don't forget to like, share, and subscribe, and hit that notification bell for more engineering insights. See you in the next one, where we discuss the second problem in which a worker has been integrated as well in the manufacturing process, thus concluding our basic problems for practice of Simio software. Please keep supporting us as we dive deeper into mechanical design and development. Don't forget to like, share, and subscribe so you never miss a step on this engineering journey with Blueprint Bazaar.